Good afternoon, CS109. We are live and back in class. I hope you had a fantastic weekend, and I hope you're ready for a little bit more probability education. Yeah, feeling the probability vibes. Okay, we are going to be learning some very cool things today. Before we jump into any of that, though, a couple quick announcements. As you probably know, problem set 1 is out. It will be due this Friday, though there is a little bit of a grace period in case you missed the deadline. Section assignments, if you don't get them today, that means something went wrong and somehow we didn't get your assignment. They will be going out today. If you can't make your time or you need a swap, see the ed post. There's more details about this. Talk about this PSET party in a second. And as always, I've gotten this habit. Oh, it should be fall 22. I've gotten this habit of putting up examples for the lecture on the problem set app. You can go to the link directly, or you can go find CS109, go find today's lecture, not the fastest internet in the world, and once the website loads, after a little suspense, you can go to lecture 4, and if you hit the little rocket ship, you can go enter today's code and follow along. Wow, man, internet, you're really stepping on my point here. Anyways, the code for today is silly owl. There you go. Not that important, but you now know. Okay. This problem set party. Hey, there's some really cool people here at Stanford. I want to tell you about 2 of them. Our PhD students, and they're interested in the future of online education. And for massive online classes, one of the things they're interested in how they can get peers working with peers. And they built a lot of really cool technology, and they want to try it out in CS109. So you might have noticed in the PSET app, there's this new button, and it has this number. That's how many people are online. Has anybody tried clicking this button? Couple of folks, if you click this button, it's like, would you like to learn with somebody else? And you're like, okay. And if you hit okay, then it kind of waits till somebody else in class hits the same button, and it'll pop up a little video for you guys. Obviously, nothing about this is for grade. It's just for fun. But you're kind of contributing to this experiment. And for massive online courses, it could be a cool feature that could change the game. In CS109, there's so many ways we can interact. It'll probably be just a small little demo. But if you come to the PSET app at 9 p.m. if you hit that button, it would be great if we could try and overload our server. And if anything goes wrong, just let us know. It's just for fun. It's not that important. But you know what is important? The stuff that we talked about last week. So just to recall, last week's focus was really on counting. And we counted lots of different things. We counted orderings of objects, we counted combinations of objects, and we put objects in buckets. And one of the big meta takeaways beyond those 3 skills, sometimes you get very large numbers. Like in the end of last class, we talked about how many ways can you order to 52 unique cards. Well, that's just 52 factorial. We learned this last week. But one of the ideas is combinations and permutations can really lead to large numbers. Like this is what 52 factorial looks like if you wrote it out. And on the end of last class, if you check the slides, there's an explanation for why that leads to a claim that if you have a particular ordering of cards with high probability, you can say no one has ever seen that exact ordering. Anyways, we talked about combinations and permutations. And then we got into the world of probability. Probabilities were numbers between 0 and 1. We started out with the 3 axioms of probability. The first 2 we talked about semantically. The third one that I promised we would talk about a little bit more later. Now is that time. The third axiom probability talks about events, and it talks about the probability of either one of the 2 events happening. So either E or F. Recall this is set notation for or. And if you say, what's the probability of either of these 2 events happening? The third axiom of probability says it's the sum of the 2 probabilities. If, and an important if, it turns out these 2 events are mutually exclusive. We mentioned this really quickly last time, but I thought it'd be worth just taking a moment to go a little bit deeper into what this assumption is saying. So all events are really sets of outcomes. And if this event is this particular set of outcomes, welcome to my little tile space. And I'm going to call this set of outcomes event E, and I'm going to call this set of outcomes event F. They're mutually exclusive if no event is in both, or no outcome is in both events. And the claim of this third axiom is, hey, in this case, calculating the probability of either E or F is pretty simple. We're just going to calculate the sum of the probability masses. Now, if you imagine like the outcome space of your world is any one of these tiles, and if you imagine they're equally likely, then we could say that the probability of E is 7 outcomes over 50, and probability of F would be 4 outcomes over 50. And so the third axiom probably says the probability of E or F would be just adding those two things together. So 7 over 50 plus 4, this is supposed to say over 50 equals 11 over 50. There you go. And that's one of the things that we assume. It works for more than 2 events if you have a whole bunch of events. If they're all mutually exclusive, so there's no outcome that's in 2 events, you can just add probabilities. We'll hit this a lot, but I just wanted to say it in a little bit more detail than we said it on Friday. Woohoo! Okay. And we'll get into this more when we practice it, but for now you should start to feel that if events have this special property of no outcomes in both events, probability of OR is going to be easy. On Friday, though, I said there's this other really intuitive law of probability which we could prove. And this is an intuitive law that we're going to use today. It says the probability of something not happening is 1 minus the probability of it happening. Okay, that kind of makes sense. But I just want to show you what a proof in probability would look like. We can prove this just using those 3 axioms. In fact, we can start with the third axiom of probability. E or not E. So either event E happens or event E doesn't happen. This is a little bit of a mind game to see if you understand mutual exclusivity. But it turns out E and not E must be mutually exclusive. Because is there an outcome where E happens and not E also happens? No, one of those two has to happen, so they must be mutually exclusive. There's no outcome that can be in both E and not E. Therefore, by the third axiom, this probability statement is just going to be the sum of the probabilities on their own. Okay, you guys following along? Either E or not happening has to cover the whole sample space, right? Because everything in the universe is either E or not E. So that is the entire universe of outcomes. And this probability of the sample space, one of the axioms of probability, axiom 2, says that this probability of something happening is 1. And at the point we're here, we can see, hey, if we're trying to derive that, we're really close. We just need to move probability of E not happening to be on its own side, in which case you get probability of E not happening equals 1 minus the probability of E happening. You know, this is what a proof in probability looks like. It probably isn't that surprising to you, and we can use these derivations we've got so far to prove further things. Okay, let's take a moment and take questions. If there's anything confusing about this, let me know. Okay, fantastic. Then I'm going to finish our warm-up with a question I'm going to give you guys some time to think about because I think it's really fun. One of my favorite things in life is serendipity, when things happen which you didn't really expect to happen, and they seem to evoke the fruit of the random tree, and they bring some good vibes to you. Okay, so here's the problem that I pose to you. Stanford has 17,000 people. I don't know how many people you're friends with. I'd say I'm friends with about 100. Maybe that's an overestimate, but you know. If you walk into a room and there's 268 random people, that's how many people were enrolled in the class at the beginning of the quarter, but now we're up to something like 315. What's the probability that someone is one of your friends? That one of the 268 people, perhaps in this class, is one of your friends? We have to make an assumption. We're going to assume that every person in this class is equally likely to be any of the 1,700 people at Stanford. If we make that assumption, we can calculate the probability that if you chose a subset of 268, that at least one person would be a friend. So that's your challenge. And I'm going to give you this pro tip. You know how the probability of E not happening is equal to 1 minus the probability of E happening? That allows you to go from the probability of E not happening to the probability of E happening. Sometimes it's way easier to calculate the probability that an event doesn't happen. This is one of those cases. So think about my question as being the probability of E not happening. I'm asking what's the chance that out of this 268 people, you don't see someone you know. Last Friday's class, we talked about outcome spaces where every outcome was equally likely. If you can utilize that, we can solve this problem. It's a pretty hefty warm-up problem, but if you can solve this, this is kind of like, you know, upper watermark of the sort of equally likelihood outcome space probability questions I'd asked you. Do you guys want to get started with this? Talk about it with the person next to you. See if you can summarize what you're trying to do and see if you can solve that problem. Okay, get to know a friend. Yeah. Okay. Let's do it together. I love this. It's such a hefty problem. So let's think about this together. I want to figure out what's the probability of not seeing anybody that you know. So out of 17,000 people, we walk into a room with 268 people. What's the probability I know none of them? And I wanted to set this up as a probability with equally likelihood outcome spaces. If you want to do that, you have to figure out the size of the sample space and the size of the event space. And you want to make sure that every outcome in the sample space was equally likely. So did anyone first come up with a sample space that they were happy with? And that's like every outcome. Like what's an outcome of this experiment too, while we're thinking about it? Yes?
Your sample space would have to be 17,000 choose 268.
So that's the size of the sample space is 17,000 choose 268. But what's one element in that sample space? Yeah, the person next to you.
If you, a random selection of 268 people.
Yeah, so every outcome in this sample space is 268 people chosen. How many outcomes are there? Well, there's all the ways you could choose 268 people from the 17,000. That's a lot. And a subset of those will be such that you don't know anybody in the class. Did anyone have a way of counting how many subsets of this set have no friends in the class? Yeah, an idea over there.
You can just subtract 17,000, your number of friends from 17,000 and choose 268 again.
So the way you could choose 268 people you don't know, you still have to choose 268 people, but instead of pulling from 17,000, we're going to pull from all the people who you don't know. How many people do you not know? It's 17,000 minus your number of friends, and I said I know 100 people. So it'd be 16,900 choose 268. What are those odds? So I know 100 people. I walk into a room of 268. What are the odds that I don't see a single person that I know? So let's do, we got math.comb. 17,000 minus 100, choose 268. Okay, and I'm just going to call that my numerator. Oh, that's a big number. My denominator, though, is going to be math.combination 17,000, choose 268. So the same number, except in this part, we're pulling from everyone at Stanford, not just the people I don't know. And if you do numerator divided by denominator, what's this 0.20 mean? It's a number between 0 and 1. Yeah, it's a probability. It's a probability that I don't know anyone. If there's a 20% probability that I don't know anyone, what's the chance that I do know somebody? Isn't that wild? If you only know 100 people on campus and you walk into a room with 268, you are very likely to know at least one person. Wow, isn't counting cool? What a time to be alive. Certainly there is this major key here. And the major key here is, oh my God, would this problem have been much, much harder if I just tried to count all the ways that I could know at least one person. Because I'd need to know all the ways that there's one person I know, 2 people I know, 3 people I know, 4 people I know, 5. Oh, that's so much. This is counting 0 people. And then the chance I know 1 or more is going to be 1 minus the chance that I know 0 people. Sometimes life is so much easier when you calculate the probability of an event not happening. Stretching or question? Looks like a good stretch. I can go for stretch too. Okay, more stretching. I like this. Okay, my daughter figured out what yoga was over the weekend, and she's like the most aggressive yoga, but she's like, yoga! Every morning. I don't know if she gets the vibe, but she gets the stretching part.
Not stretching this time. Question, if you could summarize the process in which you took to set up this problem, what would it be? Like one, like set for the outcomes, those basics.
Yeah, I always start with thinking about all the outcomes of the experiment. So like, what are all the outcomes of the experiment? And that was thinking of getting rooms of 268 people. And I tried to figure out how could I count all the ways you could get a room of 268 people. And then once I counted those, and the way I count these both gave me the feeling that everything was equally likely. Like no room of 268 people is going to be more likely than another. And once I'm there, I'm in a good spot. Then the chance is just I need to count the smaller number of people that satisfy the event I care about. The meta step, which we kind of glossed over because I told you let's just do this from the beginning, is whenever I approach a probability problem, I think, is it easier to calculate the probability directly or the probability complement of the event complement? In this case, we just started by going with the event complement. Good question. And end of review. We've got a growing tool set, and today we're going to add some awesome tools to the tool set. We're going to add chain rule, definition of conditional probability. You're going to learn the law of total probability, which is as impressive as it sounds. And the law that is so much more impressive than it sounds, Bayes' theorem. We're going to hit some of the classics in probability theory, and we're going to add them all to your probability tool set. And it all starts with one concept. In fact, if there was a central idea to get today, it's this idea of conditional probability. Conditional probability is really where probability starts to get exciting. It's how you can update beliefs. So if you observe some information, how do probabilities change? Do you guys remember we talked about dice? And when we were talking about equally likely outcome spaces, we introduced the world of dice, and we said, let's say you have 2 dice, and you want to know the probability the sum of your dice is 7. Well, we set up, here's all the outcomes of rolling 2 dice. And there's a subset of outcomes here that lead to the sum being 7. And we said that because these are equally likely events, we could say the probability of the sum being 7 was just 1, 2, 3, 4, 5, 6 divided by 36 total outcomes. Equally likely outcome spaces gave us this way to calculate the probability. But now let's change our problem a little bit. I'm going to say not that the sum comes to 7, but that the sum comes to 4. And my question for you, just to get us started, is what's the best outcome for the first dice? So the 2 dice, we're going to call the first dice dice 1. We're going to count the second dice dice 2. We care about them summing to 4. What do I want dice 1 to be? Well, I say it's just as good if dice 1 and 3, or dice 1 is either 1 or 3. Well, I say it's equally good if dice 1 is 1, 2, or 3. Do you think 2 on dice 1 is the best? Or do you think either none, more than one of these answers is right? Think about it for a moment. Don't talk to the person next to you, just appreciate. To think about this a little bit deeper, let's talk about all the outcomes where 2 dice end up equaling 4. So if you take our 36 different outcomes of rolling 2 dice, here are the 3 outcomes where your dice end up being summed to 4. If we think about the probability of the event where the 2 dice equals 4, our sample space has 36 elements in it. There's these 3 events that lead to the sum being 4. And then just using the math we learned on Friday, the probability of the event is just going to be the size of this event space divided by the size of the sample space. So 1/12. But I said the idea of today, what we really wanted you to understand, is this idea of conditional probability. And the conditional probability starts to introduce terms like this. What's the probability of some event given you've already observed some other information? And to practice, I want us to enter this world of conditional probability with the simple example of what if the first dice was 2? What's the probability that my 2 dice sum to 4 given that dice 1 is equal to 2? There's no uncertainty as to whether or not dice 1 equals 2. I'm telling you dice 1 was 2. And if I tell you what that dice 1 was 2, I've asked you to calculate probability in the world where we have information. And you can imagine when computers and probability come together, there's lots of situations where we have some information. If I tell you that F has already happened, that dice 1 is already 2, what happens to our world of probability? The first thing that happens is there's no longer 36 possible outcomes to my experiment. It's not possible that dice 1 is 1. It's not possible that dice 1 is 6. The only outcomes that are coherent with my claim that dice 1 was 2 are these 6 outcomes. Does that make sense? So once I told you dice 1 was 2, the world of possible outcomes shrunk quite a lot. Now, out of all of these possible outcomes, which ones of them lead to the 2 dice adding up to be 4? There's just this one. If you think about it, if I tell you the first dice is 2, the only way you're going to end up with a 4 is if that second dice is 2. Mathematically, we'll end up with a probability of your event going up from 1/12 to 1/6. So your probability of event happening increased. When you observed that F had occurred, that your first dice was 2, the outcome space shrunk to every outcome that was consistent with what you observed. The event space shrunk to every outcome that was consistent with what you observed. And your probability increased. Because even though there's fewer things in E and there's fewer things in F, all these events E, they're a larger ratio of things in S. Does that make sense, though? I told you, what's the chance of getting a 4? It's kind of low. But now I told you the first dice was a 2, and it's a little bit higher. If I told you your first dice was a 6, what's your probability of getting a 4? Yeah, and so if I tell you your first dice is a 2, you're like still in the game. So anyways, back to my question. If the first dice wasn't 2, but rather it was 3, what's your probability of the 2 summing up to 4? 1/6, because if the first dice is a 3, again, we'll have 6 things in the outcome space, and again, only one of those will lead to an outcome where the 2 dice add up to 4. There's only 1 dice on the second throw that could lead to a 4. It'll still be 1/6. What if that first dice was a 1? It's still 1/6, because if I observe that the first dice is a 1, the sample space has got to be all the things consistent with the first dice to be 1. So you'll get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And the event space will just be 1, 3, because there's only one outcome that leads to a 4. Doesn't matter if the first dice is a 1, 2, or a 3. They will all lead to a 1/6 probability of your sum being a 4. And this is our gentle introduction to the world of conditional probability. If we observe some information, our probabilities will change, and that changing probability is what we mean when we talk about conditional probabilities. It has its own notation. When we talk about E conditioned on F, we'll write it with this big vertical bar. And if you read that in English, it would still read as the probability of some event E given that a different event has already occurred. It's known as conditioning on F, and it's when probabilities start to get way more exciting because you can calculate interesting derivative probabilities. 2 things happen. When you observe an event, your sample space shrinks to be every outcome that's consistent with the observation. Your event space shrinks to be everything that's consistent with the observation, and your probability can change. Let's go back to our world of outcome spaces in my tiles and think about what this means. Here's event E, it's in red. Here's event F, it's in blue. Ooh, are these 2 events mutually exclusive? No, because there's these 3 events. There's these 3 outcomes where both events happen. When I talk about event conditioning on F, we're going to enter the world where F has happened. So, if we wanted to calculate the probability of E given F, we're going to take all of our outcomes, and the sample space is going to be all the outcomes that are consistent with F happening, and this numerator is going to be all the outcomes of our event that are consistent with F happening. It's like we shrink into the world of the green outcome spaces. So if you observe F, it's like F has happened. Only these things are possible outcomes anymore, because I've told you F has happened. So our outcome space will just become F, and the event space will be all these things are in both E and F. That's a little bit mathematical. What if we learned about this using a bit of Netflix, which we'll do in just a second. I want to point out a little bit, there's this notation. You'll sometimes see 2 sets without a symbol between them. That's an implicit and we'll talk a little about notation at the end of class. I want to make sure nobody gets confused. When you condition on F happening, you enter the world where F has occurred. Your sample space will become F, and your event space will become all the events that are consistent with your event space and F. Okay. Definition of conditional probability. It has this definition mathematically. The probability of E happening given that F happens is equal to the probability of E and F happening, so all the events that are consistent with F happening, divided by the probability of F happening. There you go. There is another way you could write this exact same equation. You could take this probability of F, and since it's a non-zero, or since the number between 0 and 1, so it's not negative, well, actually that's fine. You can just multiply on both sides because that's math. You can rearrange this equation and get probability of E and F happening equals probability of F times probability of E given F. We'll call this the chain rule. Some people ask, what happens if the probability of F is 0? Mathematically, won't this blow up? And let's always refer back during this lecture to what conditioning probability means. It means we've observed some events as happening. This is probability of E, given that we've observed F has already taken place. What would it mean to say I've observed F has taken place, but the probability of F is 0? Yeah, it's like if the probability of F is 0, it's impossible for F to happen, right? How can you observe it if the probability of it happening is 0? You've observed the impossible. So if you're conditioning on F, that means you're told me F has happened. It can't be the case that probability of F is 0.
Probability of E times F versus probability of E.
Yeah, fantastic. So this is, what's the chance that E happens, given that F has already happened? And this is, what's the probability of both of them happening? And it's so subtle. It's so subtle. So if you say E given F, you told me F has happened, I've entered that world. And if you say E and F, I don't know if F is going to happen. And I have to think about F happening and E happening simultaneously. Super subtle, but something we're going to hit a whole bunch today. Because that's exactly one of the most important questions to ask. Now, I've decided that this is very mathematical and a little bit hard to understand just from definition. So let's do something a little bit more intuitive. We're going to do some Netflix and learn. And we're going to think about how conditional probabilities change, and we'll get some nice intuition around it. One of my favorite movies in the world is this movie, Life is Beautiful. If it's not your favorite movie, we can talk about that, and I will convince you that's one of the greatest films ever made. Okay, just to be cheeky, we're going to talk about the probability that a user watches a movie in the context of this streaming platform called Netflix. Now, what's the sample space of somebody watching or not watching Life is Beautiful? Well, there's two outcomes. Somebody can either watch it or not watch it. And the event that I care about is that they watch it. Is the probability of the event 1/2? No, we could only do the size of the event space divided by sample space if each of these outcomes was equally likely. So it's not 1/2. So how do you think we could get the probability of somebody watching it? Assume we're Netflix. How do you think Netflix does this? They very much care about the probability that somebody watches a movie. Yeah?
Maybe they analyze like the types or genres.
Yeah. They could infer it. It turns out Netflix is so big, they can calculate it directly. They can just know the probability that you watch a movie. That was a good idea. Yeah?
They take a look at what other movies you have watched.
Yeah, that's very similar to the idea here. There is an even simpler thing that they do. That's a very good idea, but there's an even simpler thing that they can do. Yeah?
They just put it on like their front page.
They put it on the front page, and if they put it on the front page, what they can do is they can see how many people actually watch it. And so here's one of the things they do. It's even simpler than what you guys are thinking about. They go back to that core definition of what a probability is, and they just count. If they want to know the probability somebody watches a movie, they say, well, we have like 1 billion people on Netflix. I can think of each of those as an experiment, and I can see what fraction of those lead to a watch, and that will estimate the probability that a user watches the movie. And it's like they're going back to that core definition of probability. And the core definition of probability is like, if I ran infinite experiments, what subset would lead to my event? So at Netflix, 50.9 million people are on Netflix, of which 10.3 million watch this movie. You would say that probably somebody watches this movie is 0.20. Does that make sense? Even simpler than a lot of people. A lot of people have these very good ideas if we could look at what they watch for other movies. That would not give you the probability of the event on its own, but it would give you something more interesting. You guys are going down a more interesting path, which is where we're all going today. For lots of movies, you could look at the probability that somebody watches the movie. And it's just going to be counting what fraction of users watch that movie. But these numbers are not that interesting. The interesting thing is, how do these probabilities change when you observe interesting stuff like they watched another movie? And this is what everyone was getting to when we were thinking about the answer to that question. Because maybe we all care about this problem, that's where we intuitively go to first. The more interesting problem, oh, I have a typo here. The more interesting problem is, what is the probability that somebody watches this movie conditioned that I've seen they've watched another movie? So I'm going to introduce another movie that I like called Coda, which I think is fantastic. Has anyone seen this? There's 2 versions of Coda. Yeah, isn't it so good? It's freaking amazing. Okay, anyways, so now I want to change our probabilities. Not just what fraction of users watch this movie, but if I tell you that a user has watched Coda, how does that change my belief that they'll watch Life is Beautiful? And welcome to the world of conditional probabilities. And these are the more interesting probabilities because you're more attuned to the person that you're computing a probability for. If you want to know the conditional probability, here's the definition. It's the probability that somebody watches Life is Beautiful and they watch Coda divided by the probability that they watch Coda. This is just our definition of conditional probability. Both of these could be estimated using the fact that Netflix is very large. You can say this is the number of people who watch both divided by the number of people on Netflix is a good approximation of the probability that somebody watches both. The number of people who watch, and this should say Coda, divided by the number of people of Netflix is a good approximation of the probability that somebody watches Coda. And if you cancel out the number of people on Netflix and you update this, I used to like Amelie, it's still a good movie, but then I saw Coda and I'm like, I have to update. I have to update my example for my new second favorite movie. It's just so touching. Okay. If you calculate this probability, you get a different number. By the way, when you cancel out number of people who like Netflix, you're left with the number of people who've watched both. So, number of outcomes that are kind of consistent with E and F divided by number of outcomes in F of people who watched Coda. And these two tell 2 different stories. These 2 numbers we calculated tell 2 different stories, and it's going to be really hard for you to distinguish them at first. But CS109, you're going to be such a pro at this when you walk out. The first number was, what's the probability that somebody watches this movie given no other information? And this number is, what's the probability that somebody watches this movie given the information that I know they've watched this other movie? And these changing probabilities are a big deal. Okay, we can do this for every single movie. We took Life is Beautiful and we figured out the probability of that given F. And we can do that for every single probability that we calculated before. They'll mostly change. Not all of them, but most of them will change. Some will go down. If I tell you that somebody's watched Coda, it's possible for it to be less likely for them to watch a movie that you care about. Or it's possible for the probability to go up quite a lot. The probabilities can change a whole bunch when you get some information. And that's the big idea of conditional probabilities. I want to stop there. I want you to talk to the person next to you, see if you have a cool question you can ask me. Try and summarize what we've talked about and see if you can come up with something that could be clarifying. Okay, go, talk. Okay. I want a cool question. Anyone find some of this confusing? It'll be confusing the first time you see it, but it's important. So I want to take clarification questions. Great time in lecture for questions. Is this concrete example making a little bit more apparent than maybe the dice one? Okay, seeing some nodding. Any questions that came up?
I don't see how these movies are conditioned to each other.
So any movie can be conditioned.
Meaning, how do any of these relate to each other?
So for example, they might not. Star Wars and Coda could be pretty unrelated. But you can still ask the question, what's the chance that somebody watches Star Wars given that they watch Coda? Even if they're totally unrelated movies with no common themes. But I'm telling you this piece of observation that the person watched this movie, and it can change my belief of the probability that they watched Star Wars. This probability went down. It kind of tells you that those movies are unrelated. And if they're unrelated, if somebody tells you you've watched Coda, maybe it gives you information that they like that kind of movie. And if they like that kind of movie, maybe it tells you they don't like this kind of movie, so then maybe that's why the probability is going down. We can talk about lots of causal mechanisms, why these probabilities go up or down, but you can still ask the question. And when you ask the question, we can get a numerical answer. We'll get deeper into the whys as we get deeper into conditional probability. Did that help?
Yeah, I guess, yeah. So one affects the others.
You know,
Could just be interested in all of them.
yeah, some people are interested in all movies. Some people have genre preferences. There's this like deep psychological human causality that's going on. And despite all that causality, you can still ask conditional of any two events that you care about. And we should talk about that deep causality, and I'd love to get into that after class. Yes?
Yeah, what's the relationship between like conditional probability and like the complement of an event? Like, is it meaningful to ask like, what's the probability of E given that not E has happened?
Oh, what's the probability of E given not E? Ready? I tell you it's a really good question because it talks about the semantics. We enter the world where not E is true. And if you enter this world where not E is true, there's no chance that E happens. So in conditional probability, you enter a new universe where everything on the right of this line has occurred. And then you ask the question on the left of the line. Yeah.
Rolling a 1, given that you just rolled a 6?
It's not, if it's the same dice, it's got to be 0.
You're only rolling a 1.
Yeah, because if you're saying, what's the probability dice 1 is a 1, given that dice 1 was a 6? 0. It's a 6. But if there's 2 dice, you can say, what's the probability dice 1 equals 1 given dice 2 equals 6? That's totally legitimate. And if you think about multiple rolls of the same dice, I would distinguish those in some way. I'd be like, the first roll is a 1 given the second roll is a 6 or something like that. Very, very good question. Yes?
If something has so you were talking about Piech having a probability of 0, right?
Yeah.
If something has a probability of 0, does that necessarily mean it can't happen?
Yeah.
Because what's the probability that you pick a certain number on a scale from 0 to 1?
Interesting. You know, I would talk about it as being like a limit probability. We can get into that. But like, if you tell me something's a probability of 0, and if you're right, if you could be wrong. You might say it's probably 0, but you're wrong. Like the probability that the sun doesn't rise, you could say it's probably 0, and then you're wrong, and one day it doesn't rise, and you've observed the impossible. But if you're right, and it's truly probability 0, can't happen.
So it's like hard 0 versus like limit 0.
Yeah. Yes. Okay. This is also just a gentle introduction to why probability is so exciting, why we decide to offer this course of CS109, because as a computer scientist, you're going to be interacting with data a lot, and you're going to be using computers to understand that data, and language is really probability is really the language where these two things come together. You might sometimes see people referring to that simple example we did before as machine learning. Machine learning is just a nice euphemism for people who know probability and can do some data with computer science at the same time. Okay, I want to take a moment though and distinguish 3 concepts we've talked about. Unfortunately, people across the world of probability use lots of different notations for them. But we've got the probability of and of events, the probability of the or of events, and the conditional probability of one event given another. Events are things that can happen. The probability of event, what's the chance that they both happen? Different from this, what's the probability one happens given I tell you the other one has happened? Subtly different, but very importantly different. And the probability of or, saying that either E or F will happen. 3 different concepts, and I just put up those notations so you can check later and make sure you don't get confused. Somebody writes this, they mean and. If they write this, they mean and. If they write and, thank you for saying what you mean. Same, they write this, they mean or if they write or, they mean or. And those 2 concepts are very different from the conditional probability concept, which might be new for you. Okay, I was thinking about baby poop when I was writing this lecture, and so now we have a baby poop example. I have a baby. In the morning when she wakes up, there's a 50% chance that she's pooped in the night or not. And it's not always the case that she cries when she wakes up, and it's not always the case that she cries if she has poop. But if she has a poop, there's a 50% chance that she cries. So I want us to think, what's the probability that the baby has pooped and cried? And we're going to use this as a chance to try and separate our difference between probability of and the probability of or. In here, I included the definition of conditional probability and the probability of and I want to point out that this question has the word and in it. So what's the probability that the baby has pooped and cries? Think about it for a second. And then I wanted to take a moment and define some events. I'm going to do E for excrement. I can't use P. Why don't I use P? Yeah, super confusing when there's all these capital P's around. So this is going to be the event of pooped. And we need an event for cries. Why shouldn't I use C for cry? Complement. Oh my gosh. Okay, so what are we going to use for cry? We'll use like T for tears. Cries. This question is asking what's the probability of E and T? It's also given us some information. We said the probability of E is 50%, and then there's this line. The chance that the baby cries given that she has pooped is 50%. What is that telling us? So the probability that the baby has pooped, or sorry, that the baby cries, T, given that the baby has pooped, is 50%. So this is hopefully just straightforward once you recognize everything that's written as a straight example of something called the chain rule. So it says there's a 50% chance that the baby poops. And if the baby poops, there's a 50% chance that the baby cries. What's the probability that the baby poops and cries? I hear it. Somebody tell me loud and proud.
25%.
25, you can just multiply these. You know, the relationship between probability of and conditional probability is given by these two formulas, which are isomorphic versions of themselves. So this one is saying the probability of two things happening, the and of them is the probability of one thing times the probability of the other thing given that first thing. So she poops, and then she cries given that she poops. If you multiply these two numbers together, you get the and. So they're different. And condition are two different things, and there's a mathematical relationship that governs how similar they are. So the probability of this is going to be equal to the chain rule, which will be those two things multiplied together. You're exactly right. It's 1/4. Fantastic. And the point here is that people will find and conditioning complicated. Maybe we should pause here. For anyone who is thinking probability of and probability of condition were the same thing, we could pause here and see if there's a good question. Life of a parent, man. Lots and lots of poop. Yes?
The reason why they're different, like, does that have to do with like the ordering of it? Is that why they're like two separate things?
Good
Instead of having
question.
something
The ordering
different?
does matter.
Okay.
So when we say the ordering, I often think about conditional probabilities. The probability of ordering an and doesn't matter. E and T is the same as T and E. They're both happening. It doesn't matter which one. Probability of T given E is actually different from the probability of E given T. Let's think about them semantically. And these are not the same. The probability of you crying given that you pooped is not the same as the probability that you pooped given you cry. There are two different universes. One, we know you're crying and we're trying to figure out whether or not you pooped. The other one, we know you pooped and we're trying to figure out whether or not you're crying, and they're two different probabilities. So in conditional probabilities, order really, really does matter.
So going off that, in this case, if we only have the probability that they cried and then we have the probability that they cried given she pooped, we wouldn't be able to solve this, right? Is that like what you're saying there?
Yeah, there's lots of versions where I have not given you enough information to solve this. I happen to have given you exactly the information you needed to solve this. And so if I've given you, for example, if I've given you the wrong conditional probability here, there may be no way to solve that. Very good question, yes?
Where PE given F is the same as F given E, or not really?
Yeah, there are cases where these two things could be equal. It's just we don't know they're equal. But yeah, there's some cases, and it's more just luck if it turns out that they're equal. Okay. Fantastic. The chain rule is very helpful. The chain rule is what we just used, and it says the probability of two things happening is the probability of one thing times the probability of the other thing given the first thing. And it turns out you can chain rule as much as you want. If there's like the probability of event 1 and event 2 and event 3 and event n happening, you can take the chain rule and just keep going. You can say what's the probability that event 1 happens times the probability that event 2 happens given event 1 happened. And then this is some weird notation. Like, what is going on here? This is saying, what's the chance that event 3 has happened given event 1 and event 2 have happened? You enter the world where I know event 1 and 2 have happened, and I ask, so what's the question that event 3 has happened? And it kind of seems like logical. It's like the chance that event 1 happened. Okay, now I know event 1 happened. What's the chance that event 2 happened? Now that I know those two events have happened, what's the chance event 3 happened? And that's the chance of all three of them happening. That's what the chain rule is stating. Okay? Whew. You guys are ready for a law that is so useful it gets the name of the law of total probability. Are you guys ready to dive in? Let's go back to poop. So let's go back to this world where I give you the probability of the baby pooping. I give you the probability that the baby cries given that she's pooped. And now I want to ask you the question, what's the chance that when you wake up the baby's crying? And I'm not giving you enough information. You can't calculate the probability that the baby's crying. I've only told you the chance that she's pooped and the chance that she cries given that she's pooped. And I want you to just take a moment and try to invent some probability. What is the information that you're missing if you would want to be able to say the probability that she's crying? And this is pushing you to kind of invent the law of total probability. But talk to the person next to you for a second and let us do this together. Okay, does somebody have an idea? It's totally fine if you can't invent this. We will tell you. But maybe somebody invented it. Yeah, in the back.
Maybe we also need the probability that the baby cried given that she didn't poop.
Yeah, there's two worlds that can lead to her crying. Either poop, but it's totally possible that she's crying when there's no poop. And I don't know what's the probability that she cries given no poop. And no poop, mathematically, I write as E complement, excrement complement. And that's what we're missing. That's exactly what we're missing. And if we had that, what that would lead to would be the law of total probability. The law of total probability says, if I want to know the probability that my baby cried, or some event, and there's some background of events like pooping or not pooping, the law of total probability says you can figure out the probability that she cries by thinking about these two cases. Either she cries and there's poop, or she cries and there is no poop. And because those are mutually exclusive events, by the third axiom of probability, if you can figure out the probability that she cries and there's poop, and you can figure out the probability she cries and there's no poop, then you can just add up those two probabilities. So just to make this clear, I only care about the probability that she cries. But there's this background process of poop or no poop. And since poop or no poop spans the entire space, you can think about crying as coming from either this set of outcomes or the no poop set of outcomes. Is that making sense? It's a hard one, but if you get this, that's the law of total probability. You can kind of decompose your calculation of the probability of crying into these two cases, crying with poop and crying with no poop. I can't believe how many times I've managed to say poop in a Stanford class. Okay, does this make sense though, right? Your E can either come from E and F and E and not F. These two sets must be mutually exclusive because it's not possible for both F and not F to both happen at the same time. So your mutually exclusive events, so the probability space here can be added to the probability space here to get the probability of my event I care about in blue. This does generalize. Oh, by the way, once you get with this statement, each of these probabilities can then be decomposed using the chain rule. E and F can be probability of E given F times probability of F, and E and F complement can be the probability of E given F complement times the probability of F complement, just using the chain rule on both of those pieces. So that is the law of total probability. If you want to know probability of E, you can use this calculation to solve it. And there is a proof here for those who want to see the completeness, but I really think that this example is going to drive it home. The thing we were missing was the probability of crying given no poop. So let's make that up, and let's see if we can solve this. The probability of her crying given no poop, let's say that equals 1 over 8. If I told you that this was 1 over 8, what's the probability that she cries? The probability that she cries, oh, a whole bunch of bits. Good. The probability that she cries is going to be either equal to the case where she cries and there is poop. So the chance that I want the probability of crying, tears. So tears given poop times the probability of poop plus probability of tears given no poop times the probability of no poop. What's the probability of poop? Yeah, 1/2. What's the probability of tears given poop? We're told it's 1/2. What's the probability of no poop? Oh, I didn't tell you that. How do you know it's 1/2, you clever people? I know that 1 minus this probability will be the probability of its complement. And now we say the missing information was the probability that she cries given she didn't poop. And we said, there's a 1 in 8 chance of that. This probability doesn't tell us what this probability is. Being told the probability she cries given poop doesn't give us any information about whether or not she cries when there's no poop. Those are two different worlds and two different outcomes for probabilities. And if you think about this case and add in this mutually exclusive case, we have both cases where she's crying, either crying with poop or crying with no poop. There you have it, the law of total probability. What a poopy explanation. Okay, now we're going to bump this up a notch and try and do something a little bit more interesting. So, see if you can use the law of total probability and practice this world of taking a word problem and figuring out what are the probability events and what are the formulas I can use. Bacteria can cause a disease. Let's say 10% of those bacteria have a mutation which makes them resistant to antibiotics. You take half a course. Never take half a course. If they say take the full course, take the full course. Because if you take half a course, what happens? Evolution. Your bacteria evolves. And the process is basically that the bacteria that has mutations are much more likely to survive. And bacteria that don't have mutation, they're much less likely to survive. So the survivors end up being filled with mutated bacteria. But my question for you is, what's the probability that a bacteria survives? And this is a hard question. It's invoking this very complicated thing, the law of total probability, and it's invoking your ability to read a word problem and pull out all of these probabilities. Step 1, if you're finding this hard, define events. And once you have events, try and figure out everything the problem's telling you, and then see if you can solve it. So take a moment, and we will think about this together in just a moment, too. Feel free to talk if you want. Okay. Your process is first to define events. I've got an event. Bacteria has a mutation. I call that M for mutation. Bacteria survives. I call that S for survives. Now my next thing. The problem tells me a lot of information, and it defines a challenge. It says, what's the probability that bacteria survives? It wants to know probability of S. But it's given me a bunch of information. The first thing it says, 10% of mutations, 10% of bacteria have a mutation. That's not telling me a conditional probability. That's telling me an unconditional probability. It's saying that the probability of mutation equals 10%. It then gives me more information. It says the probability of bacteria survives given it has mutation is 20%. That given is a dead giveaway. That's talking about conditional probability. It's telling me the probability of survival given mutation equals 2 out of 10. And then the last sentence is probably a bacteria survives given it doesn't have the mutation is 1%. It's telling me the probability of survival given no mutation equals 1 over 100. So I know probability of M, probability of S given M, and probability S given M complement. Those are directly told. But guess what? There's 3 hidden probabilities that you're told which are not explicitly written. If I know probability of M, I also know probability of M complement. What's the probability that something doesn't have the mutation? Yeah, clever students. Good times. But I tell you that there's 3 pieces of information. I'm also telling you the probability of S complement given M is 8 out of 10. You need to know a really important thing about conditional probabilities. If you enter the world where M happens, all laws of probability still hold. And conditioned on this world M, the probability of S given M is going to, plus the probability of S complement given M is going to equal 1. It's like M is the world we've entered, where there's mutation, and in that world, all laws of probability hold. So it's still the case that probability of S plus probability of S complement equals 1 in the world where M is true. So this we don't need, but I just want you guys to know that you also have this information. Okay. So a lot of information was given to you in the problem. But what we want is the probability of S. So notice my 3 steps. 1, I defined events. 2, I pull out all the information from my problem. And 3, then I try and solve for the thing I care about. probability of S, how can I get there? It's in the top right corner. Yeah, we can use the law of total probability. There's two different background processes. Either it has a mutation or it doesn't. So the probability of S can be the probability of S and mutation plus the probability of S and not mutation. Particularly, you'd have to take this equation and replace every T with an S. And you'd have to replace every E with an M. And you get the probability of S is equal to the probability that it survives given it has a mutation times the probability it has a mutation. Do we know this? Yes. Do we know this? You can all say it out loud. Yes. Woo! Okay. Do we know M complement? Yes. Do we know S given M complement? Yes. Do we have all of the information we need to plug and chug? Yes. Yeah, okay, good times. Anyways, the law of total probability helps us solve this problem. But the really important thing is this process of pulling out events, defining what you get from the problem, and then you can just plug and chug. Okay, law of total probability. We'll get into this later when we use it more, but there is a big brother version of the law of total probability where you can have background events which aren't necessarily complements, but if background events span the whole space and they're mutually exclusive, there's a more grown-up version of the law of total probability, which we'll talk about when we need it. But I just wanted to mention it for the first time now. For now, though, I really want you to start to feel comfortable with this version of the law of total probability. Okay. It's not the real question, though, is it? We don't often care about the probability that a bacteria survives. What we really care about was what's the probability that a surviving bacteria has the mutation. We really care about the probability of mutation given survival. And you're like, isn't that given right here? We're told about the probability of survival given mutation. But someone asked a good question before, does the order and conditioning matter? And I said, absolutely does matter. If I tell you the probability survives given mutation, you don't know the other conditional probability. But there's a way to find out. And this is an idea that changed everything. In fact, one of the books I brought in on the second day of class was the idea that would not die. It's an idea that has changed mathematics. And then it changed computer science for mathematics. And it's something that's shown up like 10 times independently in my research. It is a beautiful, beautiful idea that can allow you to go from conditional probability in one direction to conditional probability in another direction. One of the great things you'll walk out of CS109 knowing, and we're going to see it for the first time today. Okay. So far, we've talked about how you can use the chain rule and the definition of probability to go between E and F and the probability of E given F. We've talked about the law of total probability, which can allow you to use conditional probabilities and get back to an unconditioned probability. And it's now time to learn how you can go from a probability of a condition in one direction and figure out the probability of the condition in the other direction. It's time for some Bayes' theorem. Okay, we're going to tell you about Bayes' theorem, but first I need to introduce you to Thomas Bayes. He was English Presbyterian minister. He invented Bayes' theorem. He didn't name it after himself. Somebody else named it after him after he passed away. And I'm going to say looked remarkably similar to Sean Astin, who played many important characters in many important movies. But that's not important right now. Bayes was thinking about this math problem, which might have popped into your mind. I care about calculating the probability of the state of the world given some observation, and I don't know how to do that. It turns out in some situations the opposite's easy. I can know the probability of some observation given a true state of the world, and how can I go from one to the other? And he was pondering this mathematical question when he came up with what was one of the most profound, important contributions to mathematics that's entered computer science, but also turns out to be, kind of reasonable given what you've learned so far. So to be clear, he knows the probability of condition in one direction. He wants to know the probability in the other direction. In the real world, it often follows that there's something unobserved that you care about inferring, and there's some observation that you see. And it's much easier to know the probability of the observation given the thing you infer, rather than the probability of the thing you care about given your observation. Don't worry too much about that, but we'll see lots of real-world examples, and I'll keep referring to that, and it'll make more sense as we go. But he was trying to figure out how you can go from one condition to the other direction, and he started with this definition of conditional probability. And I imagine he stared at it, and he had a little lamp, and the light was fading. And just before the light faded, he's like, oh my gosh, I can just plug the chain rule in to the probability of and. Because the chain rule says the probability of E and F is the probability of E given F times the probability of F. And you're like, wait, isn't the chain rule and definition of conditional probability, like, aren't they just opposites of each other? If you plug this in, shouldn't everything just cancel out? Well, there's two versions of the chain rule. You can say E and F is equal to E given F times probability of F. Or you can say probability of E and F is probability of F given E times the probability of E. Both are true. One of these totally cancels out, and the other leaves you with a deep theorem in mathematics. So he just plugged two rules into each other, and he was left with this identity, which gave us a way to calculate the probability of one conditional given the other. And I imagine the next day he was looking as like, that's beautiful. I think he just probably spent a whole day just weeping on his parchment. Just like, this is so gorgeous, I can't believe we can finally calculate the probability of conditional given the other direction. And then he's like, but wait, we can go further. He's like, this is all good and fun, but maybe this denominator term is sometimes hard to find. And he's just like, I'm just going to plug in the law of total probability. So basically, this Presbyterian minister plugs three math formulas into each other, like all known math formulas, and becomes like the most famous mathematician of all time. You're like, I could have totally done that if I was born in like, I don't know, 1705. But anyways, Bayes got there first. He figured out that you can plug all these identities into each other, and you can get a way for calculating the probability of one conditional given the other. This looks very intimidating, especially because I wrote one too many probabilities of E's. Just to make you guys feel a little bit more intimidated. It still feels like a lot of terms, but it turns out, these, oh man, how did I do that? Again, a little too excited. Technically, though, that's right, because you'd factor out the probability of F and then it would just cancel. But, but this is the actual formula of Bayes' theorem that you'll see on something like Wikipedia. This two terms, they're the same as these two terms. So even though there's a bunch of terms here, those two are the same as here. Jesus. I got my chain rule wrong. Typing too fast. Okay. And those two terms are different, but there's really only 4 unique terms you'd need to figure out the probability of conditional probability the other ways. Here is it stated correctly. I mean, Bayes' theorem is really saying that you can calculate one conditional probability the other way around. And there's 2 versions of Bayes' theorem. If you go to Wikipedia, it will quote you this one. That's basically just conditional definition with the chain rule stuck into it. But often in CS109, you'll want the expanded form, where you just take that bottom thing and apply the law of total probability. Okay. We're going to take this out for a spin. Here's a real-world example that follows the pattern where Bayes' theorem becomes so useful. You care about whether or not something is spam. So you want to know whether or not something's spam email, and you observe something about the email. In this case, I'm going to say that the email has the word dear in it. What we would like to know is what's the probability that an email is spam given it has the word dear in it, but the other direction is much easier to know. If you want to know the probability that an email has the word dear in it given it's spam, you can go through your database of spam emails and just count what fraction have the word dear in them. But in the real world, when you're trying to detect spam, you don't care about the chance that spam email has the word dear in it. You care about whether or not you're looking at spam email. And you're given the information that the email has the word dear in it. So you want the opposite of what's easy to measure. And Bayes' theorem says that we can just apply this formula to go from one formulation to another. Here's what a Bayes' theorem question could look like. And I put the formula up in the top right corner. 60% of all email is spam. You need to know the background probability of F in this case. You need that. 20% of all spam has the word dear. So that's the probability of one direction, and you'd like to know the probability of the condition the other direction. And then you need to know what's the probability that F complement. You need this probability stated. You need to have these 3 probabilities stated. Why are those 3 probabilities stated? Those are the 3 that are included here. Why is it not necessary to know the probability of F complement? Yeah, okay, that super important hint from the beginning of the warm-up today's class has come a whole bunch of times. The probability of F complement is equal to 1 minus the probability of F. So if I tell you 60% of all email is spam, 40% is not spam. If you get an email with the word dear in it, can you now update a probability that the word is spam? Sometimes you'll see this called belief. You know, like, what's your new belief that an email is spam given that it has the word dear in it? Well, let's define our events. So I'm going to say E is the event that the email has dear in it, and F is the event that is spam. And this will make it perfectly match the Bayes theorem formula. Identify all the known probabilities. In this case, you know, we have probability of F, the probability of E given F, and we have the probability of E given F complement. And then once you have those, you're just going to plug those values into Bayes' theorem, and you are done. So, interestingly, these terms in Bayes' theorem, they have names. This probability F, we call it the prior. It's your belief in spam before you saw that it had the word dear in it. So it's your belief prior to observing dear. And this is your belief after you observe dear. The chance that it's spam, and the chance that it's spam given that it has the word dear in it. And it's kind of like you're taking this old probability and updating it given the evidence of the word dear. You need to know the likelihood of the evidence. What's the probability of dear given that it's spam? And then you have to do this normalization at the bottom. We're using the law of total probability. Okay, and if you just plug this in, you would get the probability of something being spam given it has the word dear in it. One of the most canonical examples of Bayes' theorem is talking about medical tests. And this has shown up a lot in our lives now that we've had to live with COVID for like almost 3 years. Let's not talk about COVID for a second, but let's talk about SARS. And let's talk about a medical test to testing whether or not somebody has SARS. These medical tests are operating, you know, at what we call a 98% effective rate. So if somebody has SARS, there's a 98% chance that it tells you they have SARS. And there's a 2% chance it tells you they don't have SARS. So there's this truth about the person. The person either has SARS or not, but the test is not perfect. The observation you get could say this person has SARS even though they don't, or it could say they don't have SARS even though they do. This is saying that if they have SARS, 98% of the time it says they do. It has a false positive rate of 1%, which means that if they don't have SARS, 1% of the time it says they do. So probability of saying it has SARS given that they don't is 1%. A very small percentage of the US population we're going to say has SARS when this test is run. And I'm going to define these events to get us started. E is the event that you test positive for SARS, and F is the event that you actually have SARS. If we did this all together, the probability that we really care about in this one is what's the probability that someone actually has SARS given that they got a positive test. So imagine you're at the doctor and say, you just had a positive test for SARS. You're like, oh no. What does that mean? Well, it's not conclusive that you actually do have SARS. Instead, we want to know what's the probability that you do have SARS. So the probability that you actually have SARS given that you tested positive. Bayes' theorem would say that this is the probability of E given F times the probability of F. And then we would use the law of total probability to say that this is the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F. Okay, what's the probability of F? What's the probability that somebody has SARS given no other information? 0.05. Wait, 0.005. Because it's 0.5% of the US population. If it was 5% of the US population, 0.05. 0.005 is half a percentage of the US population. So we know this number too. This is also 0.05. And this number here is going to be 0.995. So 99.5% of the population doesn't have SARS, unconditioned on any other information. But how about this one? Do I know the probability of E given F? What's the probability of the test saying they have SARS given they actually do have SARS? 98%. It is 98% effective at saying you have SARS given that you do have SARS. So 0.98. That's this number over here. And the last number I need is the probability that you have SARS given that, or sorry, the probability that the test says you have SARS given that you don't have SARS. If you don't have SARS, it has a false positive rate of 1%. If you don't have SARS, there's a 1% chance that it says you do. If you take all these numbers, you can now just plug and chug. And if you plugged and chugged, you would get that there's a 33% chance that you have SARS. Isn't that crazy? You walked into the doctors, they tested you for SARS. It says, yes, you have SARS, and still your chance of having SARS is only 1 in 3. Craziness. Bayes' theorem gives you the ability to know exactly what is your updated belief. In this case, that ability to know the exact probability is very useful because there's this one really confounding factor. And the one really confounding factor is that very, very, very few people in the background population have SARS. So even this tiny false positive rate can lead to a situation where you're still less likely to have it if you test positive. I wanted to take a moment to go over intuition. Here's all people in the United States. Here's that 0.5% of people who have SARS. Most of the people who have SARS are going to test positive, but a whole bunch of people who don't have SARS are going to test positive too. And there's 2 ways that you can test positive. You have SARS and you test positive, or you don't have SARS and you get what we call a false positive. But it turns out there's so many people who don't have SARS that if you enter the world of all the people who test positive, there's still more people in that world who didn't have SARS and had a false positive than people who did have SARS and got a test. I actually thought it would be easier to make this point by drawing you a picture of everybody in the United States. I'm going to make a person here. Imagine the US is represented by 1,000 people. If only 0.5% of people have SARS, you've only got these 5 people with SARS and all these people don't have SARS. Imagine every single one of these 5 test positive. Out of these 995 people who don't have SARS, most people test negative, but 1% of them test positive. When we condition on the fact of testing positive, we enter the world where we're looking at only the people who tested positive. And in this world, there's more people who didn't have SARS and tested positive than there were people who did have SARS and tested positive. And the ratio is exactly 1/3. Isn't that wild? Bayes is a mathematical identity. I really do think of it as 2 equations put together. But there are 2 equations put together that can lead you to very surprising results. And when you get surprising results, that's often where you get powerful results. And possibly that's why this equation shows up in so many algorithms for computer science. I do actually talk about why it's still good to get tested. You can calculate the probability of having SARS given that you got a negative test result. And your chance that you have SARS given a negative test result is actually very, 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 very small. Anyways, not that important right now. I put in one last example for people who want to have a little bit more examples with Bayes' theorem. And that's where we're going to leave it for today. And in fact, I'm just going to state this, and we're going to answer it at the end. So this is something you should be able to do by the end of today. If you feel like you can't do it, take some time with it between now and next class, because this is really, really our learning goal. This is a cool example. Imagine you want to know the probability that somebody knows a concept, and all you observe is whether or not they get a multiple choice question correct. There's a lot of probabilities that people have in education theory. They say, if somebody doesn't know the answer to a multiple choice question, there's a 1/4 chance that they can get it right. Now, if somebody knows a question, they don't always get it right. Sorry, not everyone knows the concept going in. So let's say 3/4 of your population knows the concept going in. There's a chance they guess it right just because it's multiple choice. And there's a chance that they get it wrong even if they know it. Sometimes the people who know a concept will slip and just make a mistake. Could you put all this information to infer the thing we really care about? What's the chance that they really understand a concept, given that we observed a correct answer? This is the sort of thing you should be able to. What a powerful tool you have with Bayes' theorem. See if you can do this. If you can't do it, practice it. Come back on Wednesday, and we will take this to the next level. Also, on Wednesday, I want to promise you something. On Wednesday, we're going to gamble. So learn this stuff so you can come to CS109 and make some money.